if we're talking about maybe using zero-knowledge proofs, or even using something like Zcash, or if we're even talking about something like Signal, then metadata is still being leaked whenever you actually interact with any of these applications, right? In the instance of interacting with the Ethereum blockchain, even if what you're doing is interacting with a zero-knowledge proof, by the very fact of sending a transaction, you're still leaking a lot of metadata when you're gossiping that transaction, right? You're still gossiping stuff like your IP address, the time that you're actually sending in this transaction. All of this stuff is actually being leaked. And because of the kinds of machine learning that all of these kind of, the big fun guys have, they can start de-anonymizing people just based on this metadata, right? Tor itself doesn't necessarily provide anonymity against adversaries that can monitor all the ins and outs of the entire Tor network, which, when Tor was being developed, seemed like science fiction. Now, unfortunately, it's quite a grim reality, because all Tor obfuscates is your IP. There is, however, a big demand for privacy. Obviously, we're an event that's about privacy, but like in the broader context of technology and the population as well, then, Tor in 2020, you had 20 megabits a second of daily traffic, which was being spread out over 2 million users. Signal, the growth of Signal, kind of especially post-2016 and also post-COVID, more and more people are actually starting to use these technologies, but there's only so far that they can go. So, sorry, this clicker is not, do you know what? I'm just going to use my hand. So what Nym is proposing, or what Nym has built, rather, is a decentralized, incentivized Mixnet with a private credentialing system. And these are essentially the four major components of our solution to the kind of metadata-based machine learning-enabled surveillance that, unfortunately, the internet is currently suffering from. So each of these components, I'm going to go through. I'm going to focus on the Mixnet because, in this workshop, we're looking at the client. Specifically, we're looking at how you can actually send traffic through the Mixnet. But these are the other components of the system, and I'll still explain them, but I'll kind of gloss over them a little bit so we can get on with really digging into the clients and then also playing around with them ourselves. But what do we have? So we have a Mixnet, a multi-purpose Mixnet. Similarly to Tor, it's an overlay network, so it's a set of nodes that will bounce traffic between themselves, and essentially, in bouncing that traffic, you're obfuscating both obviously all of the data is encrypted, but you're also obfuscating all of the kind of metadata leakage that I was previously talking about. There is a Nym token. It is an incentivized Mixnet. So obviously, we want people to get paid. On the level of applications themselves, so the Mixnet is very much at the network layer, providing the kind of metadata privacy that I was just talking about. We also have a credentialing scheme, which is called Coconut, which is essentially able to anonymize arbitrary key value pairs. So basically, you can also then use this at the application level, in place of an identity system. And we do have a blockchain. The blockchain is called Nix, to kind of disambiguate it from Nym. And it's a open smart contracting platform which anyone can upload COSM WASM smart contracts onto. And this is the home of all of the smart contracts that currently are kind of running the Mixnet. So I'll dig into each of these. So what actually is a Mixnet? How does it work? And how does it give you the kind of metadata protections that I was just talking about? So kind of like Tor, traffic that's routed through the Mixnet goes through multiple nodes, and it goes through multiple nodes, goes through multiple hops to start unlinking the origin and the destination in terms of the IP address. And this is kind of covered in a diagram in a second. So that's the first principle. If I'm wanting to send someone a message to the Mixnet, my traffic will go through 5 hops. It will go to a gateway, through 3 mix nodes, and out the other side. And at each of these hops, obviously, this is also kind of multiply encrypted, much like Tor. We use the Sphinx packet format. So each of these nodes will essentially receive an encrypted blob they'll decrypt the Sphinx packet, and they'll see where to send it onto next, right? This is kind of, this has already been done. It's done with things like Tor. It's kind of similar to onion routing. But the second principle, or the second element of how the Mixnet works basically starts to add to the kind of protections that we already see and already kind of understand. So whilst all of these mix nodes are sending all of these packets between each other, they're decrypting these packets, seeing the destination that they need to send it to and pushing it onto the next hop. They're also sending what we call cover traffic or dummy traffic. And this is basically to make it a lot harder to do the kind of traffic analysis that you can currently do with stuff like Tor. So say, even if you have, you have an overlay network, you have all of these nodes sending each other traffic, if not that many people are actually sending traffic, then you can still kind of trace activity through this overlay network. You can still say, okay, well, sender A is kind of sending to sender B. And then you can start de-anonymizing people. Somehow I completely forgot that word. You can start de-anonymizing people based on this. You can start building up bits of metadata and start building up relationships about who these people may be, maybe what time they're sending each other these messages, what can this tell them about them. So the Mixnet, all of the nodes in the Mixnet are adding fake traffic, they're adding dummy traffic. So then it essentially retains a flat level of activity in the Mixnet, regardless of how much kind of real traffic, how many people are actually using it at any one given time. And obviously, as the more people are sending traffic through the Mixnet that's actually real, then the amount of cover traffic we have to send decreases. So we're kind of keeping like a steady state of traffic flow, right? On top of that, between each hop of the packets that are being sent, and this is something I should also add, instead of, so with Tor, you create a circuit of, say, 3 nodes, and you then send all of your traffic between those 3 nodes for 10 minutes, I think it is, unless you obviously refresh the circuit. With Nym, we actually route on the packet level. So your message is broken up into Sphinx packets, and then each of these packets is routed individually through the Mixnet as well. So then this is a kind of an extra layer of protection against bad actors or any kind of attempt to de-anonymize you by bad mix nodes. But yeah, so basically when a mix node receives a packet, it decrypts it. It says, okay, it decrypts the outside layer, right? And then it's left with another layer of encrypted information and the address of where it needs to send it to. And it will also then hold to this packet for a variable amount of time. So it applies a variable timing delay before it passes the packet on. And in combination with the previous kind of 2 things, and especially with number 2, with the cover traffic, you can then start seeing that even if you were, from the perspective of a global passive adversary, someone like the NSA, even if you can watch all of the activity of the Mixnet, then you have dummy traffic. All of these packets are identically encrypted. So you have a steady amount of Sphinx encrypted packets traveling through this network, taking multiple hops to unlink the sender and the receiver. And every time one of these nodes gets one of these packets, it also holds it for a variable amount of time. So when you start applying all of these things on top of each other, then you can see how, as a network level solution to provide metadata privacy, the Mixnet is kind of becomes a lot harder. Even if you're able to view the whole thing, you still can't really start doing stuff like traffic analysis attacks or traffic timing attacks. And also the Mixnet basically can scale. So unlike a blockchain, it can expand or it can shrink depending on the amount of traffic that's needed. Because again, actually shrinking is the most important part of scaling when there's not that much traffic, to actually retain kind of the same level of privacy and anonymity for everyone using it. And this is a visual comparison of the kind of thing that I was just talking about. So at the top, we have you as our little space invader. The top is a VPN. So to try and disambiguate the sender IP address from the receiver IP address, maybe it's whatever service you want to log into, then a VPN doesn't really do much. All you do is you pass your traffic to the VPN node, and it passes it out, right? VPNs really just move trust. So instead of the service knowing who you are, it knows who your VPN is. But, you know, VPNs are legal entities. VPNs can be leaned on to tell, you know, to tell people who they are. Also, you then have to trust your VPN provider. And regardless of how much you could trust the VPN provider, the packets that are being sent can be de-anonymized by looking at the size and the timing of them. You can look at them and say, okay, maybe this is an email, maybe this is a picture message, you know, whatever, right? With Tor, then, I wish I had a laser pointer actually. So with Tor, again, you have a circuit of nodes, so you're sending it through the Tor network, you're disambiguating the sender IP, right? So the receiver can't see that. But again, with Tor, you can still look at the ins and outs of the Tor network and go, okay, well, that pattern of packets came in at this time and it moved out at that time. We can probably assume that those two things are the same thing. And I mean, if we're, you know, obviously this is an Ethereum conference, say if you're interacting with a smart contract twice when you're using the same Tor circuit, then you can probably look at that. You can look at that traffic going through the same circuit and probably say, okay, well, there was 2 interactions with that smart contract. Chances are it's probably come from the same person, right? Again, not great in terms of being able to anonymize your network traffic from the kind of adversary that we're talking about now. And then at the bottom we have Nym. So we have you as the space invader, packets go in, they're mixed. You have, actually I'll just skip to this one, right? You're the space invader, you want to say hello to apps, whoever, on the right hand side. You send your normal packets in to a Nym client that's sat on your machine. That could be a laptop, that could be a phone in the future. At the moment, we just have desktop builds for the clients. And because this is on your, you know, before the traffic even leaves your local machine, then your Nym client will chop up this traffic, and I'll get into exactly how this works a bit later on. This is just a general overview. You chop up your traffic into identically sized root encrypted Sphinx packets. They are then sent into the Mixnet. You have multiple hops to disambiguate sender and receiver. You have the variable timing delays to aid against traffic analysis attacks. And you also have the timing obfuscation, right? So then coming out of the other side of the Mixnet, all of your packets are mixed up, identically sized, and anonymized at the level of timing and stuff. And then the client on the other end of the Mixnet will decrypt this and get your wonderful little hello message, right? So that's kind of like that's a top level overview essentially of how the Mixnet's working, right? Obviously, this is an incentivized Mixnet. We want people to get paid to be able to actually provide these kinds of services, right, of running this infrastructure. And also, if people are providing this kind of service, you know, to earn some money from doing that, right? And basically, this is where the Nym token comes in, right? So the Nym token is used for staking on mixed nodes, and this is kind of the main part of our reputation system, which is how the Mixnet is, how the constituent nodes of the Mixnet are decided upon. This is the proof of mixing rewards. Fairly straightforward, not too much we have to go into for this workshop. And so economics I can skip. The credentialing system is called Coconut. And basically our validator set will essentially create, you will pay the validator set and they will in return give you an anonymized authentication credential, which you can then basically use to both access the Mixnet, or you could use to also access other services. So instead of a login, right, it's essentially like a bearer token, but it's an anonymized bearer token. How is it anonymized? Well, these are re-randomizable. So these are kind of multi-use but re-randomizable tokens, so you can never link between uses of them. They're selective disclosure tokens, so you can prove something about yourself without actually disclosing everything about yourself, right? So this is a key use case for this would be something like KYC. You could create a credential which was essentially a proof that you passed the KYC laws for X jurisdiction, and because this credential is re-randomizable, then you could use it multiple times, right? So you could use it 7 times at 7 different KYC providers, and no one would actually be able to link between all of you, right? To say that it's just you. And the creation of these essentially is split between our validator set. So each one of the validators will produce a tiny part of this secret, and that will then be able to be reassembled into a whole credential. So even the set of validators who are creating these anonymized credentials for you can't necessarily tell which credential is yours when it's in the wild, right? So we're trying to retain unlinkability at every level, at every stage of this process, and essentially also use these to provide the kind of privacy that we're trying to provide on the network level for applications. Where is all of this happening? How are we able to do all of this? Because of the Nix blockchain. And the Nix blockchain is a Cosmos SDK chain. So it's an IBC-enabled chain with COSM-WASM enabled. So we have COSM-WASM smart contracts. What are COSM-WASM smart contracts? They are essentially a subset of Rust, which you can then compile to WebAssembly and then upload those as interactive smart contracts to live on the chain. And from our testnet, so from over a year ago, before we launched our mainnet, then we had a single smart contract keeping track of 5,000 mix nodes, a load of gateways, and all of the kind of like stake delegations that was going on between all of these things, right? So this is it's a high throughput, zero finality kind of smart contracting environment that we can work in. But, oh my God, there we go. This is a kind of an overall architecture flow of this. But obviously, this is a workshop, so if you actually want to start running traffic through the Mixnet, what components do you actually have to have in mind? How do you start doing this, right? So as I said before, access to Nym is essentially client-based, right? So whenever you want to connect to the Mixnet, you need to be running a Nym client, one of several, which I'll go into in a second. But you basically need a Nym client, and also in order to be able to connect to the network, send traffic through it, and turn your kind of normal web traffic into these encrypted Sphinx packets, right? If you're not running a purely P2P app, then you will also need some kind of a service, right? So you need some code kind of on the other side of the Mixnet that you're actually pinging, that you're actually sending all of this traffic to in an anonymized way, right? And this could be whatever. Again, because we have a client-based model, then services are just clients that listen to the Mixnet and then do something, right? So maybe you could have a service provider who makes outbound network requests for you, right? So you can anonymously say, ping your email servers or ping whatever servers. We have these already. Or you could do anonymous file storage, right? Which is a proof of concept that someone built last year, where you can essentially have a kind of an anonymized Dropbox on the Mixnet, so you access it through the Mixnet. You're not leaking any kind of metadata at the network level, and you can pull and push these encrypted packets to IPFS, right? So you essentially have a completely anonymized file storage service. And you could also, basically, it's an optional thing is you might want to run your own gateway as well, which are basically kind of like mailboxes for web clients, right? As clients go on and offline, then you have these gateways which basically will store messages for you that have come from the Mixnet. But, so which client to use, right? We have 3 different clients, and these 3 clients are basically, they're all suited to different situations, but all of them have the same core set of functions and functionality, right? So we have a WebSocket client. This is just a standalone binary that you can run on a desktop or a server, and it kind of does what it says on the tin, right? It opens a WebSocket connection, and you can ping and push messages to it that then go through the Mixnet. We have a WebAssembly client, right? So this is more useful for browser applications or basically anything that you want to do in like Node.js or TypeScript, right? Or edge computing, and it's distributed via NPM. And finally, we also have a SOX5 client. So the SOX5 client is, again, kind of what it says on the tin. It's essentially any application that you have or any kind of SOX5 proxy traffic that you want to pass through the Mixnet, you can do that with the SOX5 client. And this is actually really useful, as we will see later on, for when you just want to try out the Mixnet without actually having to write any code. So right now you can get any app that speaks SOX 5, and you just basically direct all of its traffic to that, and then boom, you can use the Mixnet with that app, right? Without having to do any code changes, which is great. And this is the kind of core functionality of all of the clients, right? So what do they actually do? Why do you need a client in the first place? First of all, they're used to determine your network topology. So basically looking at, because you're multiply encrypting all of your traffic to be decrypted at each hop, so very similar to onion routing, then obviously you need to know which mix nodes are actually there for you to be able to properly encrypt your traffic. So at each hop, each of them can unencrypt it, right? Decrypt, not unencrypt, sorry. So this is kind of, this is a fundamental aspect of what a client needs to be able to do. It needs to be able to work out what mix nodes exist, what their keys are, and how you're actually going to encrypt your traffic to pass it through. They need to register and authenticate with a gateway. And I've already mentioned this before, but a gateway node is basically it's a node that sits at either side of all of these mix nodes that mix all of the traffic between them and provide these privacy preserving properties. And you need to basically do this for two reasons. You need to essentially register with a gateway in order to create kind of a longer lasting relationship with it, so that if your client goes offline, your mobile or your desktop client, you have something sat there that's essentially acting as a mailbox for you. So then any messages you get when you're offline, the gateway will hold them for you, your client comes back online, and you pull all of those messages down, right? Seems very simple. And authenticate to a gateway. In the future, the Mixnet will be a paid service. Right now it's free. It will be a paid service in the future. And so you basically need to authenticate with a gateway to check that you paid, basically. So what else do clients do? Like I said, they receive and decrypt messages from the gateway. The client is also where the actual creation of these layer encrypted Sphinx packets actually happens, right? So you can basically just assemble the message that you want to send into the Mixnet from your app, poke it into your client, and your client will do all of this encryption for you. So you as a developer don't have to worry about that, right? It's just a process that you can poke messages to. So it makes the experience of developing and actually integrating with Nym a lot nicer, right? It will send, and it kind of takes care of sending this dummy traffic that I was talking about before, and it basically takes care of everything, right? So again, we go back to this diagram of the Mixnet. You have the U as your Space Invader. On your machine, you have one of those three clients, the WebSocket, WebAssembly, or SOX 5, depending on the use case. And that local client, you will poke your hello message to it. It will take care of the creation of the Sphinx packets, the creation of your route, and sending this fake traffic to kind of obfuscate when your real packets are being sent, to obfuscate the timing, even if someone's able to actually watch all of this internet traffic, right? It will then go through the Mixnet. At each hop, a layer will be decrypted. The packet will be held for a small while, and it'll be mixed in again with this cover traffic. And then these anonymized packets will come out, and they will come to a receiving client. So whether you're talking to a service or a desktop app, in the case of like a P2P app, say you have like a P2V version of IRC, you obviously don't need a server anywhere involved. You just need to know the address of the other person, and their client will then decrypt that final layer, and then they'll show them the hello message that we saw before, right? So, are there any questions so far? Because now what I'm going to do is I'm going to dig into each of these clients, and then we can, then there's I know you shouldn't just randomly scan QR codes, so I also put the GitHub link for the workshop notes for like the kind of practical side of this session. But yeah, do we have any questions thus far, or should I just kind of keep going? Cool, all right, I'll keep going. So, the SOX 5 client is probably the best client to actually start with if you're just wanting to start playing around with the Mixnet. And in 5 or 10 minutes, you can actually start sending traffic through the Mixnet using this client without actually having to do any programming, right? There's a bit of CLI work, but ultimately, it's very, very low barrier to entry. So what actually is it, right? So the SOX5 proxy protocol is pretty standard. Telegram uses it. Most desktop applications use it. Most crypto wallets are able to support it as well. And yeah, it's basically a very standard proxy protocol at this point. So what do you need to actually get started with it? Well, obviously you need an application to actually proxy the traffic for. So that's a Signal, Telegram, some crypto wallets, email clients like Thunderbird, right? And all you basically do is you send the traffic from that local app into your running SOX5 client, and it will be proxied to the Mixnet, right? Obviously, you need to have a local SOX5 client instance running on whatever machine you're on, whether that's a mobile or a desktop. And this service that I was mentioning before, right? This guy over here on the other side of the Mixnet, then, if you want to send, say we're going to use Telegram, right? Then if you want to actually send traffic through the Mixnet to Telegram servers and say, hey, could you grab all of my, grab all the last messages that have come for me in the last 10 minutes, then obviously you need something to actually do that network request for you. So from sending your packets from, your Telegram desktop app, they're multiply encrypted, they're sent through the Mixnet, and they get to the other side. The message that then this service would be decrypting is whatever kind of post request that you actually want to send to Telegram services that can say, hey, here's an authentication key, can you grab all these messages for me? So if you imagine the kind of surveilled internet further this way to the right of this, then this is kind of the gap, the bridge, the boundary of the Mixnet of this kind of privacy shielding, right? So then Telegram servers are over here. This guy, it will send that network request. Those servers will give it back to this network requester service, and it will then do what you just did, but opposite. So then it will say, okay, cool. It multiply encrypts the response that you got from whatever service you actually want to get it from, and it will send it back through the Mixnet where your client can finally decrypt it, and then you've just got all of your Telegram messages, right? But you've got it without actually leaking your metadata to Telegram servers. Likewise, if we're talking about a cryptocurrency transaction, you want to gossip an ETH transaction. In gossiping that, you're leaking a huge amount of metadata about yourself, the exact time that you send it, your IP address, all of this kind of stuff. So say you want to really anonymously send an Ethereum transaction, even though obviously Ethereum transactions are completely transparent. Say you wanted to do it for whatever reason, then you would do the same thing. You create and sign your transaction on your local machine. You pass that to your local Nym client. The Nym client will chop it up into identically sized, identically encrypted, root encrypted Sphinx packets, send it through the Mixnet. You send it to a service on the other end that will finally decrypt it. So, okay, cool. This is the message to gossip, and it will gossip it to whatever Ethereum node you want it to do, right? And say, and then give you the JSON RPC response as well, which is wonderful. Yeah, so that's kind of essentially what this network request, or what this third item does, right? Essentially allows a private network request to be made to outside the Mixnet. Yeah, it's not an open proxy. Why am I saying it's not an open proxy? Because there's a reason that people don't like running open proxies on the internet, because you don't know what people are going to use them for, right? And obviously, if you're running this thing, you don't want whoever, the police, whatever, to be knocking on your front door saying you're running an open proxy that was used to, I don't know, do something awful with. So yeah, basically these network requesters have whitelists. So you can think of these as like whitelisted proxy servers. So say I could run a network requester that I would only talk to Ethereum, Monero, and Zcash nodes, and that's all that I want my service to do. Anyone could pipe a request for somewhere else to me, but my network requester would just ignore it, right? And so this whitelisting is kind of a way that, yeah, people can start building up kind of different services that they want to support, basically, without the worry of just running an open proxy endpoint on the internet. Not that you shouldn't do that. It's obviously great that people run all of this stuff, but some people don't like doing it for that reason. So we want to try and help them with that. And yeah, this is basically just a GIF to show how simple it is. So this is actually just a Bitcoin wallet. You have to log out first. We can just watch this. Da, 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 da. Is it frozen? No, it hasn't. Okay, cool. So you can show that basically you just log in to your little testnet wallet. You connect through a proxy. So you've got your SOCKS 5 client running on localhost 1080. Boom, you're running through a proxy. And then you just log in and interact with your crypto wallet normally, basically. It's that simple to configure. And we'll see this a bit later on as people want to do this. So the second client that I talked about was the WebSocket client, right? Similarly, this is just run as a persistent process, and you basically just poke either binary or JSON encoded messages into it. So you can build applications to use this so long as that language is able to support WebSockets and like actually send WebSocket connections, which I would be surprised if there was one that couldn't do that, which is obviously great. And yeah, you can send either in text or binary message formats, fairly simple. And the final one, which we're very excited about, and there's been a lot of development work on this right now. So you guys are getting a bit of a sneak peek of an unreleased version of this later on. This is basically useful for if you want to kind of get this level of privacy protection that we were talking about, but from a browser or from an edge computing app, right? And we're distributing it via NPM. It's written in TypeScript, and so you can import it into any TypeScript or JavaScript app, just initialize a client from there, and then all of the data you want to send from that app, or that browser app, you can send through the Mixnet, which means you don't have to do there isn't the same level of restriction and commitment to the development process of kind of using private browser apps as there is with, for instance, something like running a hidden service on Tor that you can only access through Tor, you can only access through this one browser. With this, you could just run a TypeScript client in your browser, right? So again, send and receive JSON or binary encoded messages. This is the core of what we're calling the SDK, the software development kit, to basically get you building Mixnet applications, and very soon these anonymous coconut credential applications. And yeah, like I said, it allows for the creation of Sphinx in the browser, which is pretty wonderful. The way that we've actually constructed this as well is that it's kind of, all of these processes are very split up into different kind of like web runners. So actually, even though you're sending Sphinx packets from the browser, which you imagine would be very heavy, the app still retains the same level of responsiveness that you would kind of expect if it was running wasn't running through the Mixnet, basically. So that's the end of the formal talk side of my presentation. And like I said, basically what I have queued up next is there's some workshop notes and basically some different instructions that we can use to start playing around with these different clients. So there's just a nice set of workshop notes. If you want to access them on your computer, which I imagine you would as well, then the GitHub link is just down here. And when people are doing that, are there any questions or anything anyone has? I realize I kind of raced through a lot then, but this was just to give us some time so we could play with the clients afterwards.
Yeah. Yeah, thanks for the introduction. I just wanted to ask what's the current usage of the network? Because you mentioned, if I heard it correctly, that you already have like 5,000 nodes, right?
No. That was in a testnet.
Oh, right.
So in a testnet, we had 5,000 mix nodes. At the moment, then we have, I believe it's about 480 mix nodes, right? Mm-hmm. With, and not all of those mix nodes actually have a mix at the same time, right? So this is more of a kind of this more goes into the tokenomics of the Mixnet, but basically there's a certain kind of, there's a community delegation program which is basically like a reputation system for the mix nodes, and mix nodes are randomly selected to mix per epoch, so every 1 hour, essentially the configuration of the Mixnet will change. Mm-hmm. This is partially so people can't start building up like bad paths. If people want to start building up paths of mixed nodes that they want to try and start de-anonymizing traffic, that gets mixed every hour. And it's basically also a way to apply a certain level of kind of crypto economic pressure to retain a good quality of service, because rewards are based on mixing, not just on having a mix node that's bonded into the mixnet. So yeah, there's a quality of service based selection every hour for all of these mix nodes.
Okay.
Also, the amount of mix nodes can scale or shrink, as I've already said. We don't need more than what we currently have based on the amount of traffic throughput that we have.
Yeah.
Because actually, if you had 5,000 mix nodes, then even if they're actually sending cover traffic between each other, then you're still providing like a weaker level of privacy if there's only like 300 people using the mixnet. If you know what I mean? Does that make sense?
Yeah, perhaps.
Cool.
I guess. Yeah. A follow-up question would be like, do you consider it currently like some like attacker wouldn't like stop the network, like with those 400 nodes, and what's like the view for the future, like considering the scaling, with spamming the network, let's say.
Okay. Well, let me have a think. I mean, okay, so you don't, because it's not a blockchain, right? So you don't have to pay for gas. So yeah, we don't have a spam protection, right? Yeah. There's a couple of ways that you could start doing spam protection, right? So, but also, okay, at the moment, the mixnet's free, right? So you can spam, yeah? In the future, it won't be free. So that's inherently your own spam protection right there, right? For right now, then, for right now, I suppose basically, if you were trying to spam the network, if you were trying to spam it too hard, you would be spamming your own gateway, right? So the gateway that you're connected to would go down first, and you could stop, and that would kind of stop you spamming. That is still a problem. We are looking at kind of Sentry-based solutions or something like this for the moment with gateways, but in the future, I think a combination of like a Sentry-based model, like most kind of like blockchain validator systems have now, right? For instance, plus the fact that you'd actually be paying for the spam, kind of kills it. So it's a good question. At the moment, yeah, we're not suffering from that yet, but there are ways around it that we're looking at. Yeah.
Right. Thanks for clarifying.
No worries.
Maybe it's
for the recording. Yeah.
Okay. Maybe it's kind of stupid question, but what's happening on the other side? For example, your example with the Telegram.
Yep.
And for example, I am the receiver of the messaging, and I am not using any kind of like this mixing data or like this stuff. So can it be just like from the attacker side or from anybody who want to read the data, I want to hide, just read it from the other side on the receiver?
So, okay.
Like how to, you know what I mean? If I want to just do secret messaging to somebody, but he is just using his stuff, not like any kind of network and client. Okay. So he will receive it by himself through the like ordinary network?
Yeah, I mean, so okay, let me think about this. Right, okay, so with this example, yeah, I gave the example of pinging Telegram server, which is this guy for the purposes of just having a throughput, right? So then obviously here, the request for data from that server had to be clear text for that server to work it out, right? But what you could do is you could kind of, I know I'm getting in the way of this, but you could still encrypt, you could still poke, instead of hello, you could still encrypt that message, and then if the guy on the other side, say if you just do like a normal, whatever, PGP, right? You can still send encrypted data, and then even if, then the thing on this side, the final message it's unwrapping is still encrypted data, right? Does that make sense?
Yeah.
Yeah, so, yeah, just because you're sending a clear text message here doesn't mean you have to send a clear text message at all, right? This is really just so you can actually move, this is really just so you can actually transmit clear text messages, such as, you know, whatever, web requests or like email authentication or something. So you could actually do that at the level that only the intended receiver can actually decrypt it. But you could still send encrypted messaging as well.
Yeah, okay, I'm just trying to get it all, to think about the use cases to build something.
Yeah, no, absolutely, right? And I mean, you know, this is just in the instance of a network request that we were talking about, right? Where you have to be, but this is a very simple message, right? You could start sending really complex messages. So then if you actually want to, say if you have, there is a server that you need to talk to, but you can still send like whatever, you know, you can send literally whatever message format that you actually want. So all of the normal kind of secret sharing and encryption protocols essentially still apply here. Yeah, this is just a really simple example.
Okay, thank you.
No worries. All right, cool, right. If we don't have any more questions, then we can actually move on to the more practical side of this, if people are down for that. So, yeah, like I said, basically there's a couple of exercises here, which I linked on the board, that if people want to start playing around with these clients and actually start sending traffic through the Mixnet, we now have time to do that, basically, if people want to start doing this. So, yeah, if people are wanting to download and build the client, well, if you want to download the client binaries, then we have, if you're on a Debian-based OS or Mac OS X, then we have binaries that should work on our releases page, which you can just download now. Otherwise, yeah, you have to actually build them on a repo yourself. I have some clients on my machine which were built with Manjaro, if anyone is also Arch-based and has a USB stick, and I can give you binaries. But yeah. Yeah, sure. It's so this goes to a CryptPad link, and this is just the MD file on GitHub. Cool. Yeah, I don't really know if like recording the practical bit is necessary, maybe, but I don't know. Maybe it is. It just might not be very interesting. I mean, we can keep doing it as well, but it might just, yeah, it might just be a, are we live streaming or is it?
It's live streaming.
Yeah, cool, nice. Okay, sweet. All right, then let's have a look. I kind of thought that we would like break off and like that people would maybe want to start doing this themselves, but I suppose we could just go through the quick start documentation ourselves. Yeah, okay. All right, so yeah, let me have a look. I could basically just grab that. Okay, cool. Yeah. All right. So, like I said, our code base is built in Rust, so obviously you have to compile all of these binaries down yourself. You have to compile them, and then you're left with all of these binaries. Pretty standard. All of our binaries follow a kind of like init run cycle. So you have the binary, you initialize it. On initialization, you actually create all of your key pairs, because you have 4 key pairs. You have 2 sets of public-private keys, one's for identity, one's for encryption. And then you can also do the kind of like local configuration that you want as well. So this is, let me just check I've got the right provider. So I'll just grab an endpoint that I already know. So let's call it East Brno provider. And let's whack this in. So if we want to have a look at this provider that I just added in there, that is essentially the Nym address of the Nym network requester that I was talking about here, right? So everything needs to have an address. You need to know the address of where you're going to be sending it to in order to actually send them traffic. And this is the one that we have now, right? So then, say if I just want to actually then run this guy, no. Oh, for God's sake. And, do you know what? I just realized I'm actually running on the wrong branch. So maybe I won't. Hopefully no one actually wants to watch me compile this again. So then let's just go back to here, and then we'll break off into smaller groups. I can't get this to start. There we go. Cool. So then, yeah, let's just, who wants to actually start trying some stuff out practically? Also, because I wasn't really planning for this, so I don't mind like open all of my kind of, I don't want to start opening messaging apps on a live stream as well. So I kind of just thought we'd break off and do some, do some hands-on stuff. People fancy that.
I was trying to do it running on the Mac, but there are no binaries, so I'm not sure if I'm going to go.
Okay.